Hello again. In this session, we will learn about refraction. Now, let's look at any boundary. So, what is a boundary? A boundary essentially separates two things which are different. So, let's say in this case, two mediums are being separated. So, this side we have a medium 1, and on the other side there is a medium 2. Now, let's say a ray of light comes and is incident on this boundary. Now, let's first of all draw a normal to this boundary. Now, what can happen? We know that this ray could get reflected if the object is opaque. Let's discuss this as well. What are opaque objects? Opaque objects are objects which do not allow light to pass through them. On the other hand, transparent objects are those objects which allow light to pass through them. And then there are translucent objects. They are objects which partially allow light to pass through them. Example of opaque objects is the wall around you, the floor, or the blackboard. Anything which does not allow light to pass through it is an opaque object. Transparent objects, the examples include water, glass, etc. All the other things which allow light to pass through them are transparent objects. And translucent objects are those objects which partially allow light to pass through them. A typical example would be a cellophane sheet. Right. Coming back to our discussion, when a ray of light falls on the boundary, if the object is opaque, the ray will be reflected back. We have already studied the laws of reflection. If the ray is reflected back, the angle of incidence will be equal to the angle of reflection. But what if the medium 2 is transparent? In that case, the ray of light will enter medium 2. Now, whenever a ray of light changes medium, that is, from medium 1, it crosses into medium 2, it is said to be undergoing a refraction. Now, before we go any further, let's first define what is called as optical density. Now, recall that mass density is defined as mass per unit volume, and higher the mass density, the denser that object is. Similarly, optical density is defined, but it is defined using what is called as refractive index. And refractive index is denoted by a symbol mu. Now, refractive index for any medium is defined as the speed of light in air or vacuum. We assume the speed of light is same in air as it is in vacuum. Also, you should know that speed of light is 3 into 10 raised to 8 meter per second when it moves through vacuum. Right. So, refractive index for a medium is defined as speed of light in air is to speed of light in that medium. Speed of light in that medium. So, this ratio is defined as refractive index. So, let's think about it. What does a higher refractive index imply? You can see that the numerator in this case is a constant, which is speed of light in air. We know the value is 3 into 10 raised to 8. So the numerator is constant, which means higher the refractive index, lower the denominator. So, as small as the denominator gets, the larger is the value of refractive index. Now, what does the smaller denominator imply? A smaller denominator would mean that speed of light in that medium is less. So, the medium in which speed of light is less is optically denser as compared to a medium where speed of light is more. Let's take an example. Say I tell you that refractive index for glass is 1.5. From this information, can you find the speed of light in glass? Let's see how to do this. We are given that 1.5 is the refractive index of glass. That means that 1.5 is equal to speed of light in air divided by the speed in glass. If you rearrange these terms, you easily get that speed of light in glass is 2 into 10 raised to power 8 meter per second. So from a given refractive index, first of all, we can find the speed of light in that medium. And secondly, higher the refractive index, it means slower the speed of light in that medium. And higher the refractive index, we will say that it is optically denser. Right. So now, another thing to remember is something you will learn in waves in the later modules, that speed depends on medium. So whenever light changes medium, its speed changes. We will discuss this in detail when we come to the chapter of waves. Right. So coming back to refraction, when a ray of light hits a boundary, it could either get reflected or get refracted into the other medium. Now, when the ray gets refracted, let's show its original path through a dotted line. So say this dotted line represents the path that it would have taken if there was nothing else. Now, when it hits boundary, it would either bend towards the normal or bend away from the normal. Now, the condition whether it bends towards the normal or away from the normal depends on the ratio of their reflective indices. For example, if it is given that refractive index in medium 1 is mu1 and in medium 2 it is mu2, then the ray would bend away from the normal if mu2 is less than mu1. That is, the second medium is optically rarer as compared to the first medium. In that case, the ray will bend away from the normal. And if the second medium is optically denser as compared to the first medium, then the ray bends towards the normal. That is, this happens when mu2 is more than mu1. Right. So there are two possible paths that the light ray could take. It would either bend away from the normal if the medium is rarer, and it will bend towards the normal if the medium is optically denser. And obviously it would have gone in the straight path if mu2 was exactly equal to mu1. Then the ray would have passed undeviated. Right. So far we understand what optical density is. We see that it is measured in terms of refractive index. And we saw that refractive index is nothing but the ratio of speed of light in air is to speed of light in that medium. And also, on the basis of refractive index, during refraction, a ray of light either bends towards or away from the normal. Right. Let's now come to laws of refraction. Now, the first law of refraction is pretty much the same as the first law of reflection. The first law says that the incident ray, the refracted ray, and the normal all lie in the same plane. I'm sure I don't have to tell you that this ray is the incident ray, which is the ray of light which is falling on the medium. This line, which is perpendicular to the boundary, is the normal. And finally, one of these would be the refracted ray. So let's take this for example. So this would be the refracted ray. Right. Now, once again, if you want to measure the angle of incidence, it will be measured with respect to the normal. So, this angle is the angle of incidence. Similarly, if you want to measure the angle of refraction, then it will again be measured with respect to the normal. So, this is the angle of refraction. Right. So, the first law told us that the incident ray, the refracted ray, and the normal are all in the same plane. And then let's come to the second law, which is also known as Snell's law. Snell's law tells us that sin I by sin R, where I is the angle of incidence and R is the angle of refraction. Then Snell's law says that sin I by sin R is equal to mu2 by mu1. So this is the second law of refraction, which is also known as Snell's law. It relates, as we can see, the angle of incidence and the angle of refraction. Now, let's look at some of its implications. Now, first of all, the most common refraction that we see is between air and some other medium. So if the first medium is air, we can say that mu1 is equal to 1, because if you look at the definition of refractive index, it is ratio of speed of light in air is to speed of light in that medium. If the medium is air, then by the very definition, the refractive index is 1. Also notice that refractive index is always more than or equal to 1. This is because the speed of light cannot exceed 3 into 10 raised to 8. The speed of light is fastest in vacuum or air. Right. So mu is always more than equal to 1, and we know that mu for air is 1. So in case of refractions, when one of the medium or the first medium is air, the Snell's law simplifies to sin I by sin R is equal to mu, where mu is the refractive index of the medium which the ray of light is entering. So this is the simplified version of Snell's law, which we see in case when light ray is entering from air into a medium. Right. Let's look at a few simple examples to understand this concept better. Let's say that light is falling on a medium which has refractive index root 3, and say the medium one is air. So basically light is falling from air onto a medium which has refractive index root 3. Say it is given that the angle of incidence is 60 degrees. We wish to find the angle of refraction. Also, we would like to comment on whether the light ray bends towards or away from the normal. So let's first comment on where this light ray will go. So if we extend this line, we get the path of the undeviated ray. Now, air has refractive index 1 as we have already discussed. So we see that the medium 2, the medium in which this light ray is entering, is optically denser, and hence the light ray will bend towards the normal. So the light ray will bend this way, and this is the angle of refraction. Now, Snell's law tells us that sin I by sin R should be equal to mu 2 by mu 1. Mu 2 is the second medium, the medium in which the light is entering, which is root 3. So mu 2 by mu 1, which is 1. Now I is 60 degrees. So we see that sin 60 degree by sin R is equal to root 3. I'm sure you know that sin 60 is root 3 by 2. So if you substitute that, you have root 3 by 2 by sin R is equal to root 3, or that sin R is equal to half. I'm sure you know that sin 30 degrees is half, and hence we can say that R is equal to 30 degrees. So this was a fairly simple example. I hope it helped you understand Snell's law. Well, this brings us to the end of this session. In the next session, we will look at some of the applications of what we learned in this lecture. Thank you.